Hello everyone! Chapter 1, Learning Target 5. We're using exponential growth and decay. This is Miss Ozier.
And Miss Lahar.
And here we go. Basic exponential functions. This is the stuff you guys know. There's an exponent variable.
Yep. And the B, I don't know what pops up there. B is usually greater than 0, but the B tells you a lot about this function. Yeah, there's stuff popping up.
There is stuff. It's in white, but it's a secret.
That's okay. Those are the basics. All right, now, next slide. Because if B is bigger than 1, you have exponential growth.
Yep. And if it's less than 1 but greater than 0, it's going to be exponential decay. So essentially, if it's a fraction. We're not dealing with negative numbers here because we have exponential, so, you know, negatives could become positives, et cetera, et cetera, et cetera.
Yep. The exponentials.
You're either growing or decaying.
We're going to take it a step further because in Algebra 2, we have to start talking about like the real life applications for exponential growth equations, where you'll see these.
So these are the ones you're probably really used to seeing. It's the principal. So let's just focus on what these variables are. A is the end amount or the amount you're looking for. R is for rate. It will never be in percent. It will always be as a decimal. N is the number of times it's compounded. And T is time, usually in years.
Yep.
Okay.
And so this deals a lot with money, usually, is what we're talking about, like growth and banks and stuff like that. So the first two are just a straight flat rate, like it's growing like 5% every year, stuff like that.
Fixed.
Yep, fixed rate. Whereas the next equation, if they say it's compounded like monthly, weekly, daily, if it cuts it up into some sort of fragment of time, you have to fix the equation.
Yep. So basically anything other than yearly. And then compounding continuously, they will say those exact words. You're going to use this. E is a number kind of like pi, just to throw that out there. And P in all these is the principal or the starting amount.
E, you have a button in your calculator that it does. We'll get into E more in the next chapter, but...
Okay. So just so you know, for your domain and range of exponential functions, you could input any number into these. You could start with anything. You could technically start with negative balance. You could start with a positive balance. You can start with anything. Your range is always going to be greater than 0.
Yep. All right, so let's do some real-world applications. So if we have a population of a town and it's decreased by 4% per year and it started with 12,500 residents, which of the following is projected population in 10 years?
So because it's a year, I know that I'm going to be using the basic formula. I have my time, my rate, and my starting value, so I'm going to substitute all of those in. Remember, rate goes in as a percent, so 4% is rate goes in as a decimal, not as a percent. So it goes in as 0.04. And then we're raising it to the 10, and we go from there.
Plug it in. There's your answer.
Be careful with order of operations.
All right, word problems. Don't get scared because there's a lot of words in this, but here we go. We have a stock price of Wind Power Incorporated is increasing at a rate of 4% per week.
Ooh, that's important.
Yep. Its initial value was $20 per share. On the other hand, the stock price of Gerbil Energy is crashing, losing value, at a rate of 11% per week. If its price was $120 per share when Wind Power was $20, after how many weeks will the stock prices be the same? Model them with an equation and then find where they graphically are equal.
Okay, so let's do the equations first. We have the Wind Power Inc. starting at 20. It's increasing, so I'm using the plus 0.04, and it's weekly, so we have to be careful there. On the other hand, the Gerbil Energy is losing 11% per week. Okay. Now for this one, because they were both the same week and week, we can model it like this. If one was weeks and one were monthly, we would have to deal with that other compounding formula. But because they were the same, we were able to just use this straightforward formula, graph them, and then you find where they meet.
They intersect. So that would mean after 11.5 weeks, we would have equal amount of money in both of these companies because that's what they were asking.
There we go. A population of wombats was growing at a constant rate of 5.1% per year. We want to determine the percent growth in wombat population will be over a decade of time. Now, these are different because they're not actually asking you how many wombats are there going to be. They're asking what the percentage of growth is. So we're still going to use that formula. However, we're just going to focus on this part.
Yep. So they want a decade of time. How many years is a decade? 10. So that's why we plugged in 10. If you evaluate that, you're going to get 1.64. And if you think about it, 1 plus R is your rate of increase. So we have to figure that out and just subtract 1 from that value in order to get what our actual percent growth rate is.
Right. Percent growth should always be what's over 100. If you're growing, it's over the one that you started with. So that would be the 64% in this case. You don't have to show this step. We're just trying to show you where the logic of the 64.4 comes from.
So over a decade, these wombats would have increased 64.4%.
Whoa.
Ugh, I hate bats. All right, let's go the other
Gross.
direction. So what if we wanted to know monthly? Like, how much do these bats grow monthly?
Oh, wombats. Okay, so we have the same exact thing, but monthly would be a year divided by 12.
Yep.
So every month, they're increasing by a rate of, ooh, be careful here. Get rid of your 1.
Yep, get rid of the 1, and that's going to be a 0.4%. Okay, which does kind of make sense, 5.1% per year, so a 0.4%.
Right, it should be smaller. We're doing little months.
Yep.
Little months, itty bitty.
Mm-hmm.
Okay, so now we have another one. A constant rate of 22% every 5 years. Then what is its percent growth rate over a 2-year time span? So let's first focus on what would happen just a single year before we start talking about 2 years. So 1 year is smaller than 5 years, clearly.
Yep.
So we're dividing.
So we're going to divide our exponent. So if we have, the exponent is representing 5 years, and I want to know per year, I'm going to divide by the 5 in order to get per year.
Yep.
So we get that. So I know that there's a 4.1 yearly increase.
Look at us go.
So then if they want to know, well, what happens after 2 years? You would just multiply it by itself again, or just raise it to the second power.
Yep. So you can just keep that, we kind of created it so that it was 1 year. You could multiply that by 2. Or you guys are probably smart enough to just figure out, oh, if it's 1/5, well, 2 years would be 2/5.
Mm-hmm.
Same concept because of power of exponents.
So again, you would have about an 8.3% growth.
Look at us go.
Mm-hmm.
All right, number 5. Seth's parents are very generous people, and they gave him $5,000 to invest for his 16th birthday. He has 2 different options, 4.5% compounded annually and 4.6% compounded quarterly. Quarterly would be every 3 months, people, just to be clear. So here would be the straightforward function for 5,000, 1 plus the rate of 4.5% every year.
Okay. Now option B, because it's compounded quarterly, that n value is a 4. Okay. So we use the equation 1 plus the r over the n value raised to the nt, 4 times t in this case.
Look at us go.
So then after 6 years, they want to know which account has more money, because it's all about the money.
Yep.
So when you use the equations and plug in 6 for that t value, you see that clearly option B is the moneymaker.
The moneymaker by roughly $67.
It's still $67 that he didn't have before. And I mean, $5,000 was pretty good anyway.
Absolutely. I would
Okay.
like my parents to do that for me, and I'm a grown-up.
Yep.
A loan shark. Oh, goodness. Don't ever get involved with a loan shark, people.
Yeah, we're
Okay?
showing you how bad this is. So let's say you borrowed $1,000 to cover your gambling debt.
He charges 35% annual interest. That's ridiculous. And he compounds it continuously.
Which
so
means all the time.
all the time. So that's where you use that PERT formula. That's how we will refer to it. So how much at the end of 1 year and 2 years? So for your $1,000 that you borrowed, remember this is a number like pi. It's a button in your calculator. After 1 year, so we substitute 1 in, you're going to owe, because the 1,000 you already owed, you're going to have to pay him $419 in addition to what you owed him to start with.
He's really rocking your monies right now. So then if you, that's out of order, but whatever. They want to know after 2 years. So you do the same thing, plugging in 2.
And you almost, you owe him double
Yep.
what you originally did. And that was only after 2 years. Oh my goodness, it's terrible.
Don't get into gambling, isn't it?
No, it's a
But
bad
anyway.
idea. That's the moral of the story. All right, so that is a quick gist of exponential equations and growth and decay.
Just use your formula, know what those variables mean, just plug it in and evaluate.
Have a wonderful day. We'll see you in class.